Good evening. My name is Sai Vivek Nanduri and this is my science project. First, I would like to talk about Hermite polynomials. The topic being discussed in the first is Hermite polynomials. Hermite polynomials, denoted by the function hn of x, are a set of orthogonal polynomials over the domain minus infinity to infinity, with weighting function e power minus x squared. We will come to this weighting function. Hermite polynomials hn of z, we can write it in the mathematical form by using the contour integral of hn of z is equal to n factorial by 2 pi I contour integral of e power minus r square plus 2rz into t power minus n minus 1 dt, and where this contour integral encloses the origin and is traversed in a counterclockwise direction. We can have a look at some of the first few Hermite polynomials in the sequence. The first five Hermite polynomials are written. The first five Hermite polynomials are written below here. H naught of x is equal to 1. H1 of x is equal to 2x, and H2 of x is equal to 4x squared minus 2. H3 of x is equal to 8x cubed minus 12x. H4 of x is equal to 60x power 4 minus 48x squared plus 12. This line here, the straight line that we see, that we can count, that is h1 of x, and the slight curve is h2 of x in black, and then again we have the red curve. This one is h3 of x, and the last w-like shape is h4 of x. One more important point that can be noted is that the hn of 0, when substituted in this whatever values that we get, these can be referred to as Hermite numbers. So the Hermite numbers would be 1, 0, minus 2, 0, 12, such on the sequence would go. Here we can see the Hermite polynomials can be represented in the Schiffer sequence, where j of t is equal to e power t squared by 4 and f of t can be written as half t, which gives the exponential growing function exp of 2xt minus t squared, which is the same as sigma n is equal to 0 to infinity hn of x t power n by n factorial. Okay, now moving on to the using that part, we go to Taylor series. We can see from Taylor series that hn of x is equal to dou by dou t of n exp 2 power xt minus t squared, which is obviously from the Schiffer series, the growing exponential function where t is equal to 0, and then we get e power. We can write this as e power x squared into dou by dou t of n e power minus x minus t whole square, which is just simple mathematics. And then since dou of f of x by minus t by dou t is minus 1 of this, we write minus 1 power n here, and we change it to hn of x is equal to minus 1 power n e power x squared dou by dou x n e power minus x minus t whole square, which we can arrive at this final thing, minus 1 power n e power x squared dn by dx power n e power minus x squared. We are derivating with respect to x. Okay, now following on, we can define the two operators. O1, where O1 is same as minus e power x squared d by dx of e power minus x squared, and O2, which is e power x squared by 2 into x minus d by dx of e power minus x squared by 2. Now, using mathematical derivation, we can easily prove that O1 is equal to O2, which we can write. From this equation, we can arrive at these following conclusions. Exp of 2xt minus t squared is same as this one we wrote in the first itself, and then we arrived at this in between. hn of x is equal to minus 1 power n ex squared dn by dx power n by e power minus x squared, but which we proved this is equal to this, so we can also write hn of x is equal to e power x squared by 2 x minus d by dx of n e power minus x squared by 2. See that a couple of more notes that we can important. Hermite polynomials are orthogonal to e power minus x squared. That was the weightage function in minus infinity to infinity domain. Hermite polynomials satisfy symmetry condition. Hn of minus x is equal to minus 1 power n hn of x. We could see that in the graph. And the recurrence relations are also satisfied. These ones are hn plus 1x is equal to 2x hn of x minus 2n hn minus 1x. Hn of x is equal to 2n hn minus 1 of x. These are the following things. Okay, now we are coming back to Laguerre polynomials. This is the second topic that we will be discussing today. Laguerre polynomials are solutions to their solution, the ln of x denotion to the Laguerre differential equation. We will come to this Laguerre differential equation later, having nu is equal to 0. Okay, this nu equal to 0 is an important condition. Laguerre polynomials can also be defined by contour integral again. The contour integral in this case, ln of z would be given by 1 by 2 pi I contour integral of e power minus zt by 1 minus t whole divided by 1 minus t power n plus 1 dt. Here contour gamma, it may look 1 minus t might look like where the contour is being enclosed. However, we must note that it is enclosing the origin and not the point t is equal to 1. As we were discussing before, the Laguerre polynomials are fundamentally the solutions ln of x to the Laguerre differential equation, having nu is equal to 0. What is the Laguerre differential equation? I said we would come to that. Okay, so here it is. The Laguerre differential equation in its most general form is x y dash dash plus nu plus 1 minus x y dash plus lambda y is equal to 0. This is the Laguerre differential equation. Now, to find out Laguerre polynomials, we must have the constraint nu is equal to 0. When we substitute nu is equal to 0, this is the equation that we get. This is a more special case of this equation and is the one that we use for solving Laguerre polynomials. The Laguerre polynomials are given as solutions to this equation. X y dash dash plus 1 minus x y dash plus lambda y is equal to 0, where nu is equal to 0 in the above equation. Now, we'll come to see how the Laguerre polynomials shape up. So the Laguerre polynomials are given by the sum. We arrive at this by this sum. ln of x is equal to sigma k equal to 0 to n minus 1 power k by k factorial and then nk x power k, where nk in brackets is denoting the binomial coefficient nck. And we get, this is the sum of the Laguerre polynomial, and we can find off ln of x like this. So now we can have look at a couple of ways we can represent Laguerre polynomials. One is we can represent Laguerre polynomials using Rodriguez representation in this form, which is ln of x is equal to e power x by n factorial d power n d by dx of n power x and e power minus x. That's the equation for Rodriguez representation of Laguerre polynomial. Sorry. And then here we can also write a generative function g of x comma z for Laguerre polynomials in this fashion, where g of x comma z is equal to exp of minus x power z by 1 minus z, where this is exponential growing function, whole divided by 1 minus z. And this gives rise to this 1 plus minus x plus 1 z plus half x square minus 2x plus 1, so on. We will look at the way that this. Okay, so as I was saying, the first few Laguerre polynomials we can see are L0 of x is equal to 1, L1 of x is equal to minus x plus 1, L2 of x is equal to half into x square minus 4x plus 2, L3 of x is equal to 1 by 6 into minus x cube plus 9x square minus 18x plus 6. We saw this from the generating function that we drew in the previous board. And also the graph that we draw up for this we can observe here, where this straight line symbolizes L1 of x, L2 of x is given by this curve, and L3 of x by the next red curve here, and finally we get L4 of x by this curve over this black curve here. And a few concluding notes on Laguerre polynomials. One, Laguerre polynomials satisfy the recurrence relation just like the Hermite polynomials. N plus 1 ln plus 1 x is equal to 2n plus 1 minus x ln x minus n ln minus 1 of x is the recurrence relation satisfying for n plus 1, and for ln x it's x ln dash x is equal to n ln x minus nl minus 1 x. These are the two recurrence relations that the Laguerre polynomial satisfies. And one more side note is that solutions to the initial Laguerre equation, differential equation, which was, if you recall correctly, x y dash dash plus nu plus 1 minus x into y dash plus lambda y is equal to 0. Yeah, the solutions where nu is not equal to 0 in that equation, they are called associated Laguerre polynomials, and they are denoted by ln k of x. Let us have a look at the third topic that we are going to be discussing today. This is inertia matrix. We are talking about rigid body inertia matrix here. So when a system of particles is assembled into a rigid body moving in the 3D space, then we are able to characterize the moment of inertia of all the particles in scalar form as a matrix of inertia, or an inertial matrix. This inertia matrix appears in the calculation of the angular momentum, kinetic energy, and resultant torque of the movement of the rigid body in 3D space. we will be taking a look at how the inertia matrix appears in these calculations. First, let's move on to angular momentum. Okay, so let B be a skew symmetric matrix, any skew symmetric matrix that can be constructed from a vector small b, where we write b of y is equal to b cross y. Then b is of this form, where the elements of b are 0, minus bz, by, bz, 0, minus bz, minus by, bz, and 0. Now we construct a skew symmetric matrix following this principle delta Ri, where delta Ri is the relative position vector, and we're able to construct it from Ri minus C. If given this definition, then angular momentum we can define as capital L is equal to minus sigma I is equal to 1 to n mi delta Ri square into omega, which we can also write as IC into omega. The IC here is the symmetric inertia matrix that we are looking for. Symmetric inertia matrix, as you can see, the IC is equal to minus sigma I is equal to 1 to n mi delta Ri whole square. Now, let us look at how we use the inertia matrix in the calculation of the kinetic energy as well as the resultant torque. Okay, so first in the formulation of kinetic energy, as we have studied in class, we have three terms for kinetic energy, where the middle term is actually, we can assume when center of mass is at origin, it gets cancelled, nullified, and we're left with two different terms. We came to find that EK, the kinetic energy, can be written as a combination of the rotational kinetic energy as well as the translational kinetic energy. Okay. Now in this notation, we are able to bring in the delta Ri skew symmetric matrix, and we can see here evidently from this next step that half omega into IC omega plus half mv square c gives the kinetic energy, where IC once again is the matrix of inertia, the inertial matrix. Okay, so moving on to the torque. In the calculation of torque, it's simple. From Newton's second law, we get tau is equal to sigma I is equal to 1 to Ri minus R into mi ai, where mass of all the particles and A is the acceleration of that ith particle. But interestingly, we can write ai is equal to alpha into Ri minus R plus omega into Ri minus R plus AR, and by introducing once again the delta R skew symmetric matrix, the delta Ri skew symmetric matrix, we are able to write tau as a function of this as minus sigma I is equal to I equal to 1 to n mi delta Ri whole square into alpha plus omega into minus sigma I is equal to 1 to n mi delta Ri whole square. Now as we found from previous examples, this is equivalent to the IC matrix, so we write it as tau is equal to IC into alpha plus omega into IC into omega, where IC is the inertial matrix that we have been observing. That is all for the presentation today, and that is the end of the video. Thank you.